So hi, this is Minhajur Rahaman. So I'm a postdoc at the Open University of Israel. And today I'll be talking about what constraints do we have for magnetar progenitor models for these PRS sources that we have been hearing so much associated with fast radio bursts. So for the purpose of this talk, I'll focus on the best studied case and try to see what kind of inferences we can get. So when you talk about the best studied case, we have the famous repeater R1, aka FRB 121102A. And now for this particular source, we already know that it is localized in a dwarf galaxy at a redshift of 0.19, which gives you a distance to the source of around 973 megaparsec, which is close to a gigaparsec. And in this image, you'll see that there's a cross here. So this cross just shows that you have the location of the PRS in the off nuclear region. Okay. And this is a zoom in version of the PRS and the FRP imaging that has been done. So this paper appeared just 2 days back. So now, of all things, we know that for the PRS associated with FRB 121102A, core specialty is known to a high degree of precision. In fact, the best one that we have. So given this, what else do we know about the PRS? So we know from imaging at 5 gigahertz that we have an upper size limit to the PRS, which is around 0.7 parsec. So this source also shows radio scintillations, which means we also have a lower limit on the size of this particular source. And given we have an idea about the spectrum of this source, and assuming that the emission that you see from the PRS is of synchrotron origin, we can do an equipartition kind of an analysis. And from the equipartition analysis, you can get an equipartition radius. And if you estimate the equipartition radius, that comes out to be 0.1 parsec, which sits very comfortably between the lower limit and the upper limit that you have. So putting all things together, one thing that can be said for sure is that these sources that you are talking about are very compact. And in fact, the compactness of this source is a very important clue in deciding what kind of magnetar progenitors will be able to satisfy. So when you talk about a magnetar kind of a progenitor, what is the physical picture that you have in mind? So here is a schematic of what we have is that we have a central magnetar engine, and then the central engine is actually embedded within an expanding supernova remnant. So this orange portion or the circular region that you see corresponds to an expanding supernova remnant. And what the magnetar does is it initially gives rise to a PR plasma wind, which is cold, which then gets confined and trapped within the supernova remnant. And it is this hot magnetar wind nebula which is giving rise to the PRS that we see. So this is the candidate. So this shaded, darker shade of green, which is labeled as magnetar wind nebula. So this is your candidate for the PRS that you are trying to explain. So what is the one thing that is clear from this picture, from this very basic schematic? So if you talk about the size of the magnetar wind nebula, the size is the same as the size of the supernova remnant. That means if in your model you have a way of constraining the energetic of the supernova remnant, that is akin to saying what is the size of the magnetar wind nebula itself. So let's do that. So as a test case, let's take the most popular candidate that people have talked about in the context of fast radio burst, aka the millisecond magnetar. Now the list of references that you see on screen is not meant to be exhaustive, but is just there to show that it has been a leading candidate, a popular candidate for almost a decade. So you can now put this whole millisecond magnetar idea to the test. Okay, so you have a millisecond magnetar. So you know that if the period is 1 millisecond, you know what is the rotational energy. It is 10 to the power 52 ergs of energy, right? And now, given it's a magnetar, the spin dyne time scale is going to be on the time scale of few months at best. So that means within few months, most of the rotational energy that it started with, which is 10 to the 52 ergs of energy, is going to be lost. And where does this energy predominantly go? It goes into boosting the supernova remnant expansion. Okay. And now you ask this question, okay, we have a size constraint of 0.1 parsec. For a millisecond magnetar progenitor, what time it would take for the remnant to expand to that particular radius? Okay, a simple question. And if you calculate the numbers, it comes out to be less than 3 years. And they say, wow, in less than 3 years, this remnant has already expanded to a size of 0.1 parsec. And remember, the first burst from this source, as the name suggests, was in 2012. So I've seen this source till now and still being monitored. It has already been over a decade. And as far as the predictions of the millisecond magnetar model, this had to happen within 3 years. So this clearly makes millisecond magnetar untenable from the size constraint alone. And in fact, you can see right from the size constraint that any combination that you can think about the supernova energetics, for example, the superluminous supernova or ultra-swift supernova, anything that gives you large expansion speed is going to reach this particular remnant size in shorter times. So you can ask the other question, okay, given the size, what would be the smallest expansion velocity that can be achieved? So the smallest expansion velocity, by definition, would need that the supernova remnant has an energy which is typically less than the typical supernova energy, and hence the sub-energetic supernova. So instead of having a 10 to the power 51 ergs of energy, you have 10 to the power 50 ergs of energy. And on top of that, if you have a massive ejecta. So if you combine this, you have less energy and more mass, you make the expansion slow. And inevitably, if you make the expansion slow, you are reaching ages in the range of few decades. Okay? So the point is that if you have this sub-energetic scenario, you have more space to breathe in terms of time. You are in other cases, you just have to be on time to catch this sub-parsec structure. Okay? So now that we have advocated for this particular sub-energetic scenario, you say, okay, at most this remnant or this wind nebula will be 0.1 parsec for up to a century. That's fine. But what is the powering mechanism? So I have talked about the size itself, but it is a luminous source. So for a luminous source, you need some powering mechanism. So from the equipartition analysis, we can also estimate something called the equipartition energy. And what is the physical idea about the equipartition energy? This is the minimum energy that is required for the source to be powered. Okay? And that minimum energy comes out to be 10 to the 49 ergs. Huge. So that means unless the energy in this magnetar wind nebula is 10 to the 49 ergs or more, you cannot power the PRS at radio band. Okay? So to understand whether this kind of power or energy is available in the magnetar wind nebula, what you need to say, okay, so what are the two channels of powering the nebula? So one is obviously the rotational channel, and the other channel that you already heard from is the internal magnetic field decay channel. Okay. So now let's look at this plot. What this plot shows is that on the x-axis it shows time since birth, and on the y-axis it shows the energy content in the nebula. And this equipartition energy or the minimum energy of 10 to the 49 ergs is shown as this horizontal line. So that means for any energy content or energy curve which is above this horizontal line, you have sufficient energy in the nebula to power it. Okay. So if you look at the rotational channel, which is this purple line, so what happens for this line? You see that initially the power in the nebula is increasing. Why? Because it is before the spin down time. So most of the power in the nebula is being deposited by spin down. Okay. And from that point onwards, what you have is adiabatic loss. So that's why the curve comes down. So you have this injection phase, which saturates at the typical time scale of energy injection, which is the spin down time scale. And beyond that, the curve comes down because now that in the nebula is not sitting there static. It is embedded in a supernova remnant. If the supernova remnant itself is expanding, the hot magnetar wind, which is confined, the supernova remnant is confining it, is actually getting energy from the PDV work done due to the hot gas. And that's the reason you see this decrease in energy. Okay. So for the rotational channel, what is the one thing that is clear? So within about a decade, you have quenched your energy. That means if you want to power the PRS from the rotational power channel, you cannot do it for more than a decade. So that means the only way to make this viable is to have your internal magnetic field decay. And this is an illustration, this red curve is an illustration of the internal magnetic field decay, which says that now if your internal magnetic field decay has a typical decay time scale, which is much, much larger than the spin down time scale, say hundreds of years, then you can make this line above this horizontal line and sustain this emission for longer time. So this is a logarithmic scale, okay? So now, so this is the idea that we are proposing, that if your age of the system is few decades and the rotational energy is actually quenched within a decade, the only way you can sustain the PRS is if you have this internal magnetic field decay. And inevitably, in this kind of a picture, what you have is that you have first the nebula being dominated by rotational channel, and then there is a characteristic time in which the energetics of the nebula switches from rotation domination to magnetic decay domination. As in thing, it is a very important conceptual framework because most of the earlier works which talk about internal magnetic field decay took the decay time scale to be around few months at best. So if your spin down time scale is at the order of few months, if your decay time scale is of the order of few months, there is no actual switching between the domination. So in fact, the idea in those models is that you have all the energy deposited within few months from birth. But then if you deposit all the energy within few months from the birth of the magnetar, that energy only degrades with time. So by the time you are at the time scale of a decade, although you satisfy the size constraint, effectively there is no energy left in the nebula to power the PRS. Okay? So based on this, now if you combine the subenergetic scenario, if you combine the other constraints that you have from scintillations and everything, you get this blue strip, which satisfies the constraints for the PRS associated with TRV1102A. And in this blue strip, you will see that there is clear prediction for the spectrum. What is the prediction? That if you look at this red dotted line, this is the self-absorption frequency. And if you look at this dashed blue line, this is the cooling break. So this makes clear prediction that not only is this source at most a century old, but if you go as observers and try to look at the spectrum, there's a clear indication of a cooling break at around 100 gigahertz and a self-absorption frequency at around 200 megahertz. Okay? Now, I want to spend some time in saying that, okay, you say there is a PRS, what is the typical luminosity? You say, okay, L nu is 10 to the power 29. And you are seeing this as a frequency of a gigahertz, right? So nu L nu is actually the power output. So which gives you 10 to the power 38 ergs per second. Humongous as it is still less compared to the bolometric luminosity. So where is the bulk of the bolometric luminosity coming out? It is at the cooling break. So in fact, then the cooling break is the point at which most of the bolometric power of your nebula is being tapped. And this is an important fact that needs to be restated, that the location of the cooling break is not some just arbitrary thing that, okay, it's fine, it's a cooling break there, but the cooling break is the place where most of your energy is being tapped. So in your radio service, you are actually sensitive to L nu M. So you measure everything in terms of Jansky, milli-Jansky, micro-Jansky. So this is actually specific flux. Okay? But if you have to look at the energy output, you have to look at the peak of nu L nu. And the peak of nu L nu is at the cooling break. So that's a very important thing that needs to be taken. And that is a motivation of why this cooling break matters. And now we can ask this question, okay, given we have so many hyperactive repeaters, how come from the population viewpoint, we have only these few PRSs? Why don't we see in many of the cases that we have pointed at telescopes and, okay, we have some upper limits? The point is, if you look at this energy content in the nebula, 10 to the power 49 ergs of energy, that is present in the nebula and above. And if you look at the strongest internal magnetic field, if you take internal magnetic field of around 10 to the 16 Gauss, this is 2 times 10 to the 49 ergs of energy. So that means almost all the internal energy that you have needs to be channeled into the power of the nebula. And at the same time, the energy density in the nebula for the non-thermal particles needs to be very high. So if the energy density is not very high, you do not have energetic particles to emit. Okay, so that means if you have an energy and your energy density needs to be high, you need things to be compact, and hence a compactor source size actually gives you higher energetic particles. And the third thing is what I mentioned earlier. Say suppose you had all the energy in the nebula, and you say, okay, I don't see anything in radio. Maybe in radio, the cooling break is very far from that band, right? Because most of your power is being put out at the cooling break. If the cooling break is at a much higher frequency, you have less power in the radio. So even if you have more power in the nebula, that is not effectively seen at the radio band. So you need some critical value of the radio frequency compared to the cooling break to be satisfied, such that some of that power actually seeps down at the radio band. So this is a work in progress, and roughly these are the kind of criteria that we are going through to understand PRS on the population level. So with that, I think the one of the most popular models of FRB, aka the millisecond magnetars, actually fails at explaining the PRS sources. At the same time, if you're now thinking in terms of powering mechanism, the rotational channel is quenched very quickly. And it appears that the magnetic power channel is the one that can sustain this emission for decades. And the combination of this sub-energetic supernova and this ultra strong magnetic field decay, which is giving rise to this PRS, comes with definitive predictions that can be tested using observations. So to end, I'll end on this quote by George E.P. Box that essentially says that all models are wrong. Some are useful. So with these predictions and the forward modeling that we're trying to do here, let's make the magnetar model useful. With that, thank you for your attention.
Thank you, Minhajur. And it's a really interesting talk. I think we have time for taking one or two questions. Yeah, Sunil.
Really interesting talk. I was just wondering, so you mentioned the nebula has the order of like 10 to the 49 ergs of energy. Does this translate in any way to thermal emission? So if I were to point JWST at the source, would I be able to see infrared emission?
So the point is that we're talking about optically thin synchrotron radiation. So all this energy is in the nebula, and this emission is in the optically thin zone.
Okay.
But the consequence of this amount of energy and the compactness of the size already has a prediction for the self-absorption break, right? So below the self-absorption break, we can talk about the steepening of the spectrum. So this is exactly what we are talking about. Although the spectrum that I showed you is for optically thin slow cooling synchrotron spectrum, one of the definite predictions of that at very low frequency is this self-absorption break. And below self-absorption break, you have this steepening, which is expected for a black body kind of behavior below self-absorption.
Okay, then next Yogesh.
Hi, Minhajur.
Yeah.
I have slightly disconnected question. So all the PRS works, they consider very young magnetar,
Yeah.
right? So for example, in your work, you say up to about a century or so, we can have this PRS emission. And the only observational link we have for FRB is from our galactic magnetar. That's one magnetar which is fairly old, about 3.5 kilo years. So how do you reconcile these two?
Because they don't have, so this galactic magnetar doesn't have a PRS. See, for PRS formation to happen, I already told you it has to be embedded in the supernova remnant. And the reason that it needs to be young is that this magnetar wind needs to be confined within the remnant. So for the galactic magnetar that we have, it's very old. So the remnant associated with it has faded. And the energy density that is required for the magnetic field decay is in the range of 10 to the power 16 Gauss and Moore. So for the galactic magnetar, even if you take a dipolar field strength of around 10 to the 14, which is what is measured, at most the magnetic field strength of a few times 10 to the power 14. It's nowhere close to the 10 to the power 16 Gauss of internal magnetic field that is required to power these sources.
Yeah, no, that's still for the PRS. And in our own galaxy, we also know some young magnetars, just a few hundred years old. And we don't see any yeah, very bright burst from those.
Yeah,
high-
so again, that depends on the nebular energy and also the cooling break. So one of the things that even for Crab pulsar, like the amount of, so the bolometric luminosity is so much larger than what you see in the radio. The reason being most of this energy is being powered in a different band. In fact, the only magnetar wind nebula that we have is this candidate Swift J1813-4-0846, for which we did see a magnetar wind nebula, but that magnetar wind nebula predominantly emits in X-rays and not at radio. And for this, again, the explanation is that the magnetic field strength is high enough, but for the PRS, we are actually pushing the limit of the most strong, ultra strong magnetic field that can be thought of.
Okay, thank you.
Okay, then I think we can discuss offline more. And let's thank our speaker again. Thank you.